Now, if this were an actual, piece of muscovite, the chain would go on and on and on and on, and these sheets would continue for a long time and just continue to be separated by these large potassium atoms. Why is that important? This is because a crystal lattice, part of the definition of a mineral is that it has to have a definite chemical formula. This is the definite chemical formula, the definite crystal structure for muscovite mica. So this is repeating and predictable. If we have a piece of muscovite mica, we know that the crystal lattice looks like this. So when we're talking about cleavage, muscovite mica is a really good example of cleavage. We'll get into that when we're done talking about cleavage, but smooth, flat, often parallel surfaces, and then it occurs because of alignments of weaker bonds within the crystal lattice. There's clearly going to be some weak points in here. And the cleaving will correspond to the planes of atoms that are less tightly bonded to each other compared to the rest of the structure. And because the crystal lattice will always be the same, always, 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 this is predictable and repeatable, and thus it's extremely diagnostic. So let's grab our piece of mica so that we can take a look at this huge, spectacular piece of mica. Okay, so mica cleaves extremely readily. This is specifically a phyllosilicate mineral, which we can get into the different categories of silicates at another time, but you can see that there are these parallel planes of cleavage on the material. And you can also see where it's kind of actively, so this is, I think, the best way to observe cleavage when we're trying to understand it on an atomic level.